Gaussian noise versus Laplace noise. In the last two lectures, we learned about mean squared error and mean absolute error. While learning about those, we learned that mean squared error is related to Gaussian noise and mean absolute error is related to Laplace noise. In this lecture, we are going to clarify what exactly is Gaussian noise and what exactly is Laplace noise. With this, you will have more clarity on what is the difference between these two distributions and how they are related to mean squared error and mean absolute error. First of all, when I say Gaussian noise, that means your noise is following Gaussian distribution. Similarly, when I say Laplace noise, it means your noise is following Laplace distribution. I'll show this in a pictorial manner first so that you understand what exactly are these two distributions, and then we'll go to the mathematics and understand what are the specific differences. Okay, let us see, this is the graph. Just assume that you have some random variable, a continuous random variable x. Then we'll see how will the distribution look like if it is Gaussian. Okay, I'll take a different color with, let us say, with red color. I'm going to draw Gaussian noise. So if it is a Gaussian distribution, how will it look like? It will be a bell curve, right? That is how a Gaussian noise should look like. So the bell curve will be something like this. It will come like this. It will have a bell shape, come down, and it will go back, right? This is how a bell curve will look like. This is what is a Gaussian distribution. Instead of Gaussian, if it is a Laplace distribution, how will it look like? If it is Laplace, the difference is, one, its peak will be more sharp. Here it is a bell curve. Instead of that, the peak will be sharp like this. The second thing is, both the tails will be thicker than the Gaussian. Gaussian has a very thin tail. Coming to Laplace, tail will be thicker and peak will be sharper. So let us draw, if it is Laplace distribution, then it will look something like this. It will have a thicker tail, sharper peak. It will come down. I'll draw once more. It will have a thicker tail coming to a sharper peak. Then it will come down to the other side and again a thicker tail. So this is a Laplace distribution, right? This is the case of Laplace distribution. Next thing is, as of now I just showed you in a graph. Here from the graph there are two things you want to note. One is that coming to Laplace, it is having a sharper peak instead of Gaussian, which is having a bell curve. And coming to the tail part, Laplace is having a thicker tail while the Gaussian is having a thinner tail. The next is, what on the mathematical side, what is the significance of these things, right? We'll write the formula for both of these, the probability distribution function. Then we'll clearly understand what are the differences. So if x is a random variable, x is your random variable, what is the probability distribution function for a Gaussian? If it is a Gaussian, it will look like this. Probability of x given mu and sigma square. What are mu and sigma square here? Your mu is the mean of your distribution. Whatever is the mean of your distribution, that is mu. So mean shows the center of the distribution. What about sigma square? Sigma square is the variance of your distribution. What does variance denote? Variance denotes the spread of your distribution. Mean denotes the center and variance denotes the spread of your distribution. What is the formula or the probability distribution function, a probability density function for a Gaussian distribution? Coming to Gaussian distribution, probability density function will be 1 by root of 2 pi sigma square e raised to minus of x minus mu the whole square divided by 2 sigma square. I'm not explaining this function. We already had this discussion in our Gaussian distribution lecture. Here I want to compare between Gaussian and Laplace and see what are the differences. One thing, only one thing I want you to note here is that coming to the probability density function of Gaussian, you can see that error, that is, I'm saying error is Gaussian, then in that case your error is falling off quadratically. That is because of this term x minus mu whole square. Here you can see the term minus x minus mu the whole square. Because of the squared term here, your error is falling off quadratically. This is the first point I want you to note from this particular formula. Next thing, let us compare the same thing with a Laplacian. So here it is a Gaussian distribution. I'll mark it as G. If the same thing is in a Laplace distribution, then what is the difference in probability density function? Let us say my probability of the random variable x is my random variable, given mu and b. What are mu and b in Laplace? In case of a Laplace distribution, mu is your mean, same case as in Gaussian. So what does this show? Mean shows the center. Second thing is, what is this b? B in case of Laplace distribution, this is the scale. So when I say scale, this is also a measure of spread. So you can relate this thing with whatever we mentioned as variance here. This variance and this scale, both are showing the same parameter. Both are showing spread of the distribution. So the first parameter mu, it is showing the center of the distribution. Second one, which is b, spread, it is scale, it is showing the spread of the distribution. So you can relate this b with the sigma square. Variance is also showing spread, b is also showing spread. Okay. What is the formula for Laplace distribution? It will be 1 by 2b into e raised to minus of mod x minus mu by b. This is the formula for Laplace. The same way you previously noted that error is falling off quadratically in case of Gaussian, I want you to note here that in case of Laplace, error is not falling off quadratically. Instead, it is falling off linearly, because here you can see error is falling off in the terms of x minus mu. This is a linear term, because of which the whole point I'm showing you this mathematical formulation is, I want you to understand from here that why error is falling off quadratically here and why error is falling off linearly here. This is the main difference I want to show between a Gaussian and a Laplace distribution. Coming to the shape, we already discussed that coming to Gaussian, the shape of the curve will be a bell curve. But in case of bell curve means the top part will be smoother. It will have a smooth bell curve. Peak will be rounded. You can see the peak of the Gaussian is rounded. And what about the tails? They will be thin tails. So what does this thin tail mean? I'm again and again saying thin tail, thin tail. What does that mean? That means in this particular distribution, extreme values are rare. That is, if you have a mean, most of your points will be around the mean. The values that are extreme, going here and there, those points will be very rare. That is what I mean when I say tails are thin. So it's not just about a picture. What it means is the points which are far away from mean, they will be very rare in case of a Gaussian distribution. What about the Laplace? In case of Laplace, you have sharp pointy peak at mean and heavy tails. What does this mean? When I say I have heavier tails, this blue one, Laplace distribution, when I say heavy tail, that means outliers are more common. Coming to a Laplace, you may have more points which are outliers. So this is what heavier tail means. So you can simply say Gaussian is sensitive to outliers and Laplace is robust to outliers. This is the point. Okay. So on the other things, on the mathematical side, what are the other differences that it introduces? So we are seeing it more from gradient descent perspective and all. So when you see that, one point is coming to Gaussian. We saw that the gradient is always smooth. So this already we had seen in the MSc lecture that how this is smooth. Okay. So we know it grows with error magnitude. One point that is important here is, what happens with the gradient? Where are we going to use gradient? We are using it in gradient descent. In gradient descent, what exactly is the purpose of gradient? Gradient decides how much should you adjust your value in each iteration. According to the gradient, you will adjust the parameters of your model. Coming to this Gaussian distribution, because gradient is smooth and it grows with error magnitude, what happens when the error is larger, your convergence to the actual mean, that will also be faster, because if your error is large, your gradient will be larger, and the change that you make in your parameter, if you have some parameter p or p1, in this particular p1, because the gradient is larger for larger error, you will make larger changes, that is change by a larger numeric value, and you will converge faster. What in case of Laplace? Laplace, we know it is piecewise constant, that is plus or minus 1. It won't change with the value of error. Even if the value of error is very large, still gradient of Laplace will be constant. It will be plus or minus 1. Because of this, you can also understand that it is harder to optimize. Why is it harder to optimize? Let us say you have some particular parameter P1 in case of Laplace. Here, even if you make very large errors, your gradient will be plus or minus 1 only. Because of this, your convergence to the mean will be smaller, that is slower. That is the speciality with Laplace. So how do we relate this to MSE and MAE? That is mean squared error and mean absolute error. Gaussian noise assumption leads to MSE loss, mean squared error loss. Why does this lead to mean squared error loss? Because Gaussian noise has the exponent which is in quadratic, which is related to mean squared error. But in case of Laplace, this noise assumption leads us to MAE loss, that is mean absolute error loss. Why is it? Because exponent here is linear, and the main point is when you do maximization of likelihood, that will lead to these particular errors, right? So this is the main thing about Gaussian and Laplace. One more thing you can keep in mind is where exactly do you use Gaussian, where exactly do you use Laplace. So Gaussian is generally common in all physical measurements, these sort of things. So maybe thermometer measurements, sensors, these things, Gaussian is more common. Why is it common? Because there is a central limit theorem which says that in case of, we'll go to central limit theorem in the next lecture in detail, because there is more to explain there, then only it will be clear for you. Okay, for now understand that in many of the general experiments, if you take any of the independent and any of the IID random variables, independent and identically distributed random variables, what happens is, irrespective of the initial distribution, the final distribution will always come out to be Gaussian distribution. Or in simple terms, you can understand that if you take any random experimental data, chances are that your experimental data will always follow a Gaussian distribution. Any of the general data, if you take, there is a very high chance that it will follow Gaussian distribution. Why is it? Just think about this. If you take simply height of the people in your area, if you take a large number of people and you see the heights of all those people and mark it in a graph, what happens? A lot of people will have heights around the mean. There will be very less people who are having very less height. Similarly, the number of people having very high height will be very less. That is, both the tails will be thinner. But at the mean, there will be a lot of people who are having the average height. This is how generally all the data will follow. So this is it about Gaussian. Gaussian is generally seen in all these situations. What about Laplace? Laplace, it is useful in environments which are having spikes or occasional large deviations. Why did I say that? It is because when you have occasional spikes expected, that means you are expecting outliers here. When you are expecting outliers, your tail should be thicker. There should be more chance of outliers. That is where Laplace distribution is used. So depending on your data, whether it is expecting outliers, not expecting outliers, all these conditions you have to take in consideration. Then you have to decide whether it is Gaussian distribution or it is Laplace distribution. Whether you should use MSE as the error function or should you use MAE as your error function or loss function. In the next lecture, we'll go to central limit theorem. We'll detail about what exactly is central limit theorem, how it is working. This will give you more clarity about all these concepts, Gaussian distribution, everything. Okay.